Hello, back EMF. You've probably heard of it. If you've ever had any real involvement with electronics or kind of switching anything under load, it's an effect that can cause high voltage spikes, which, when unwanted, can quite often cause ongoing damage or destroy semiconductors. Now, this is a little rough test rig I've put together to demonstrate some effects. I'm almost out of sight at the back. I've got a 12-volt battery. For an isolated power supply. Just pull the wire off it. A little bench supply. That's also supplying somewhere around 12 volts. Relay and just a random transformer picked up, which I'm using as an inductor to demonstrate the effect. This side's a little 555 oscillator with a couple of transistors on it to drive the relay. So if I turn the bench supply on, the relay starts clicking in and out at a regular basis. And I've got scope probes connected to the output of the 555 to show the timing synchronization. I've got one connected to a resistor, 1 ohm resistor that's in line with the transformer winding. Now I'm using the 230 volt secondary of this, so I don't take excessive amount of currents and don't do anything too catastrophic. So that's about 30 ohms, so it's taking less than half an amp when it's connected to 12 volt power. Then I've also got a high voltage scope probe on the terminal I'm switching through the relay. Through the relay there, this orange wire will be the positive feed from the battery when I connect it, and out of the relay the white wire goes to one side of the inductor. Then the other side of the inductor goes back to battery negative through the resistor. So the battery negative is connected to the scope ground terminal, and also the scope ground is connected to the 555, though that is otherwise a separate circuit, specifically to try and avoid the high voltage spikes getting back to the 555. I think there's something a bit dodgy on that bit of breadboard, but as long as the relay keeps working, that's all that matters. Remember, this has only got a 12 volt supply from a battery. Let me just grab the meter just to verify. The battery has been fully charged recently, so it could be up to about 13 volts, I suppose, but it shouldn't be much different to that. So going on the battery terminals, I have 13 volts. Just to show, if I go, I don't really want to connect the orange wire yet. But so it's the same circuit. If I connect it to the battery positive and there, you can see that's the negative back there. Or there, because there's no current flow, it doesn't make any difference. So that's 13 volts and about 30 ohms. In fact, I'll just verify that. Somewhere in the region of 30 ohms resistance on that secondary winding. Sorry, primary winding. There we go. 33 ohms. So not particular high current and not particular high voltage, only 13 volts. Now, common sense says from that only a few volts across the contacts of a relay that's rated to switch at least 240 volts, I can't remember the exact rating, but they're quite high, shouldn't have any detrimental effect. I'll tell you what these are in a second. I can read it. Right, it's rated with 10 amps at 250 volts AC. But when I connect that positive, you can see some quite dramatic sparking on that relay contact. Every time it opens, that's a back EMF effect from the inductor. And I've also got the scope being screen recorded whilst I'm doing this, so I can synchronise that afterwards to show the effects of the voltage and current. The basic cause is an inductor stores energy in a magnetic field. Even a bit of wire has inductance, but normal wire connector wiring at normal type frequencies, the inductance is so small it's usually irrelevant. But start making coils and putting them on, especially with a ferrous former or core, and the inductance and the magnetic field strength can get very high, and it can store a lot of energy. And the closest analogy is water hammer. You know the effect if a water tap or valve is fully open and closes suddenly and you get a thump in the pipes. That's the same effect, if you like. The inertia, the stored energy, or stored magnetic field if you like in this, the stored energy tries to maintain the flow in the same direction. And the result is a sudden very high pressure or high voltage spike. If you look at the scope screen, the yellow is the 555 timer output on pin 3. When it's high, it's turning the relay on. When it's low, it's turning the relay off. The blue line, the centre trace, is the current in the inductor measured across that 1 ohm resistor. And as you can see, the current gradually ramps up whilst the contacts are closed, then drops away when the contacts open. There's a slight delay between the 555 output turning off and the relay turning off, because it's just a it's a mechanical device. So there is a slight delay. But you can see the point the contacts start to open, the current suddenly starts dropping. And as that happens, the voltage, which at that point has been slightly positive, in the purple trace, the third trace, that is centred on the dotted line that's just underneath it most of the time. That's been slightly positive. The contact opens, the current the energy has to go somewhere. It tries to keep flowing, and it causes, if you like the effect, it's the analogy to water, because of a vacuum at the end of the pipe you just cut the supply from, rather than pressure of the one that's feeding it. The voltage reverses. Now that purple plot is on a scale of 200 volts per division. So it's going from slightly above the reference line there to somewhere around 5, well, you can see it's about, it's probably getting on for 400 volts at a little plateau, and sometimes 500 or 600 volts more. And the only thing limiting it to that plateau is the arc on the relay contacts, because they start to arc as soon as they open. And as long as the arc maintains, that limits the voltage to some extent. And there's a little tiny spike as it loses energy and stops arcing. And if I change the time scale to magnify just the time around that, you can see the effect better. It's a bit unstable. The random variations in time. I'll freeze one and let you have a better stable look. If I can stop the clicking for a minute at that. It's a bit annoying. Once the little power supply discharges. Right, that's better. Okay, so if you look at the oscilloscope screen now, the yellow line dropping is when the relay, the 555 drive circuit turned off. And that's on 2 milliseconds a division. So after about 7 or 8 milliseconds, the relay contact started to open and the current started to drop. It was maintained momentarily by the arc and then dropped off completely. And the result was a very high negative voltage spike on the output, several hundred volts. And that's on an iron core mains transformer, which is not good at high frequencies. Some things would give them vastly more. Now, if that was being driven by a transistor rather than relay contact, as it is, there's a very good chance that the transistor would be destroyed at the first opening or first switch off due to the extreme voltages. It would just be burnt out. Now, they're not generally made to stand that type of voltage, or not something you'd expect to be okay switching a 12-volt device, as this is doing. Now, if I put it back on again, there's several ways to avoid that problem, and the simplest and commonest one is a flywheel diode. And I say that the current is trying to keep going in the same direction, and it can't easily when the contact opens. But as the voltage is reversing as it tries to maintain itself, you can put a diode backwards across the coil and all the nasty high voltage spikes just go away. You can see it's now a completely clean switch off. I mean, the ramp up's changed because this core's now getting magnetised because all the current's in the same direction all the time. So it's affecting how it ramps up. It is still ramping up, it's just a different curve. So the bit you can see as it is looks flatter. But you can see with that, there's no high voltage spike, everything's nice and clean. If that was now being switched with a transistor, as long as it could handle the current safely, it would not have a problem. The downside with that in some circumstances is that the current will now circulate for a little bit longer than desired, just a scope probe, after the controlling device is turned off. Now, a lot of the time that doesn't matter, but with some things where you're trying to switch things at a very, very high speed, it can cause a problem because things will just stay held in on an electromagnet slightly longer than intended. There are the other options for working around it are such as a voltage dependent resistor, the VDR. And what these do, they're a metal oxide device that doesn't conduct up to a certain voltage and then over a fairly narrow range breaks down and conducts. But as long as the current's not excessive, it doesn't do any harm, it just produces a bit of heat. And if I connect that across it, this one by the way, it's normally rated at 30 volts working, which means it'll break down to about 50, 60 volts probably, or start to break down. And again, if I put that across, it's nice clean, and you can see the purple trace switching from power to nothing. It's going to be kicking reverse a fraction because this is kicking down to about 30 volts or so reverse. But as long as the circuit's designed to take it, it's not going to cause a problem. But you do need a higher voltage transistor than if you're using a diode. That's the downside, but the upside is you get a much faster switch off because the current is being killed, the energy in the coil is being dissipated harmlessly quite quickly. I wonder if you can see that effect. At the moment, the current is dropping off 3 subdivisions to the right of the centre line. Let's compare that to the diode, see if it's possible to see the difference. Just get the diode the right way around, or else it'll short the thing out. Just about. You can see that the current's now somewhere around half a subdivision later when it drops. So it's not a lot. That's on 2 milliseconds. So it's a fairly short time with this particular inductor. I mean, I know on some things like very large industrial inductors like motor fields and things like that, that you can actually see the current die down if you just disconnect it and let it flywheel for 2 or 3 seconds. There can be massive amounts of energy stored, and if you're trying to control one of those quickly, it needs fairly special drive circuits. But so for normal relays and valves and things like that use solid valves or solenoids that you won't be able to drive, a diode or a VDR and a bit high voltage transistor will work quite nicely. Another option is a resistor and capacitor, an RC snubber, which I haven't actually got out. I'll have to just grab the bits for that. Right, I'm not actually sure what value this capacitor is. It looks something like reasonable, but I can't read it. Oh, I can. 0.22 microfarad. It's 224. Right. Now, the way an RC snubber works is the capacitor will pass the high frequency component to the resistor without passing low frequency or DC. And a very common off-the-shelf component that combines capacitor and resistor has values like 0.1 microfarads and 100 ohms. So you can get a wide range of different ones. So if we connect this in, I'll do it that way around so I can hold the capacitor insulation a bit easier. Really good connection there. Might also be killing the capacitor. I've not a clue what ratings these capacitors are. They only be using for low voltage circuits. No, I can't get a connection on that. I think I'm actually resonating the coil a bit with that. You can see it's having an effect, but it's actually magnifying and stretching the pulse. I think the values are appropriate as well. You can see it has a definite effect. It takes the edges off. I think the resistor value is too low, only 15 ohms. It needs to be a higher resistor. It's seeing it as capacitive rather than the capacitor just coupling the resistor in circuit. You try a higher value. I've actually got some of the proper things somewhere, but not to hand. So I forgot to get anything set out for this. Right, it's 100 ohms. I mean, normally these are used with AC. AC circuits, because the properly designed ones can be connected across AC power without any harm. So they can be connected across a coil whilst it's powered, and they just absorb the spike when the contact's feeding it open, without any other real effect. It's minimal power dissipation. Right. Oh, it's the same thing. Okay, that's interesting. Never actually looked at one on the scope before, but that is very, very strange. It's somehow resonating with the switching frequency. So no, okay, forget that one. Right, now, of course, the other thing is with back EMF, if instead of just dissipating the energy or letting it freewheel through a diode, you reroute it somewhere else, then that's the basis of a lot of switchboard power supplies, or a lot of excuse me, secondary switches anyway, like a buck converter or a boost converter. Just reroute the output with an appropriate circuit, so the current maintaining itself provides a continuous power or pulses of power each time it's switched off to feed the output circuit. And that also has parallels in liquids. There's an ancient form of pump called a ram pump or an inertia pump. Just don't let that stop. Thank you. It basically consists of a pipe running from some kind of reservoir or tank, a cistern, just a length of pipe that allows water to run through it and build up speed. The water gets to an exit chamber that's got a metal disc resting in it on a support. And once the water flow gets to a certain speed, it can lift the disc, and the disc pops up and hits the hole in the top of the chamber and blocks it. That causes a water hammer effect, and the chamber also has a second flap valve that will allow the pressure out to a second pipe or reservoir, a standpipe that just stores it through gravity, through its own weight. And with nothing more than that, it can lift water up quite a distance into a high reservoir, or for irrigation or storage in a house or whatever. And it's a very, very similar principle to a switchboard power supply. Interrupting the flow into an inductor and allowing the inertia, the stored energy, to cause a spike or maintenance flow to a high voltage. Now, this, as I say, this quite often it can be destructive and damaging. If it was these relay contacts were in use in a machine that was doing something like that, they're probably already noticeably discoloured and pitted, and after a while they would be destroyed, because every spark is a burst of superheated plasma, and the air's ionised and converted to plasma, and some of the metal from the contacts, because of the extreme temperature. Well, the temperature in the sparks, thousands of degrees, I would think, in that little arc. And it does wreck relay contacts in a relatively short time. And I mean, this is, as I say, it's only a low current circuit at 12 volts, so it's only less than half an amp. Now, if you're switching a serious inductive load, it might only last a few thousand operations, and the relay will be burnt out. Whereas putting a flywheel diode or VDR across the load, or across the or even put a VDR across the contacts as well, as if you don't want to do it across the load, no, it's better across the load, because it avoids the spikes travelling in the connecting wires and possibly being coupled to other things. But something that stops the arc means the relay can last thousands or millions of operations, or tens of thousands of operations at least, rather than a relatively small fraction of what it could possibly do. Now, there are also some other fun effects you can have with this. I mean, one of them you've almost certainly seen in cinema. It's used in no end of films. I think Highlander was one, for example. You see a sword fight or something like that when the two fighters draw the swords across each other and get a shower of sparks from them, or arcs where they touch. If I replace the relay with two pieces of metal, preferably steel, that are connected where the contacts are, then those arcs are produced every time there's a slight break in the contact. And steel tends to produce some nice sparks when it is exposed to an arc. So I'll just connect this in. I've got two wires on these in preparation. I do remember to do that bit. So disconnect the positive from there. It's a bit long, it doesn't matter. Connect the negative to the white wire that feeds the coil. I don't need the 555 circuit or the relay chatter in the way. This is just being used as a connecting terminal now. That orange wire is not used. The battery negative is still connected, but I'm now going to connect the positive to. Oh, that's why they were stripped wrong. I was originally going to do it the other way around. So the battery positive goes to one wire, negative is still connected back to the coil. At the other side of the coil and it goes to that one, and positive goes to that one. So now, hopefully, right, not enough power for any really dramatic sparks, but you can see actually on the oscilloscope, it's going crazy. I expected a bit more out of it than that. That resistor's probably not helping, that's limiting the power. Also, if I wanted it really dramatic, I'd probably use the two primaries in series rather than the secondary to just get more current through it. I could try that. They'll have to pause for a minute and put soldering on them. Connecting both windings in series to give a bit more resistance, because the winding resistance is going to be very, very low. It's going to take extreme current. Could burn that bit of thin wire up. In fact, it could burn any of the wires up, and the battery can provide probably 100 amps or so. So I have to be a bit careful with this and not leave anything connected too long. That's going to damage things. I don't want to actually wreck anything. These terminals aren't particularly clever, but should give it a good enough connection for now. It may also cause an extreme voltage across the, well, almost certainly will cause an extreme voltage across the transformer primary, back driving it like this. So it might cause some marking there. I don't really want to wreck the transformer. That's better. Right, I'm going to turn the light out for effect. Computer screen slow outside, but anyhow. Got similar effects. Yeah. Slow fighting arcs. That's how you get it. Not going to keep doing it too much because, as I say, the currents are quite high. and I don't want to damage anything. But I hope you see the effect and how dramatic back EMF effects can be. I hope that's been interesting. And if you enjoyed it, please hit the like button, and please subscribe to the channel if you want to see more like this. Okay, and thanks for watching.